Our next speaker hails also from UT Austin Astronomy Department as a graduate student, almost fourth year. Sydney Sherman, Agent Sheila, will be talking about maybe not the most energetic, but about the most massive things we might find in the universe. Her fun fact is she is a self-identified mosquito magnet. On a 1-week trip to the Ukraine, she was the benefactor of over 200 mosquito bites, while everyone else on the trip apparently got less than 10. Let's welcome to the stage Agent Sheila.
Yeah, it's horrible. I do not recommend 200 mosquito bites. They bit me through raincoats, jeans, everything. It was the worst experience ever. My mosquito bites had mosquito bites. Do not recommend to anybody. Anyway, so I'm going to be talking to you about the most massive galaxies in the universe, which is my research that I do here at UT. But before I tell you about how to find the most massive galaxies, I should probably give you a good reason of why you should want to find these things. We have this sort of standard picture of how structure forms in the universe. So we believe that small things form first, and then at later times, larger things form out of those small things kind of coming together. Unfortunately, or fortunately for me, massive galaxies kind of break this mold. Well, they don't really break it exactly. They sort of bend the mold. So we believe that massive galaxies, the most massive galaxies in the universe, formed extremely early in the history of the universe. So our universe is currently about 14 billion years old, and we believe that the most massive galaxies in the universe formed the majority of their stellar populations within the first 3 to 4 billion years after the Big Bang, and then they stopped forming stars altogether. They haven't really formed any stars since. And if we can understand sort of how these extremely massive systems formed so early on in the universe, then maybe we can constrain theoretical models about how structure forms in the universe, how galaxies form and evolve, and how the universe came to look like it does today. So that's the reason why we should study these things. But in order to study them, we need to know what to look for and where to find them. So galaxies come in all different shapes and sizes. Up on the top left, we have spiral galaxies with their beautiful arms and their really unique structure. We have interacting galaxies, elliptical galaxies, which we also call red and dead galaxies because they're sort of red and they don't form any stars, so they're kind of dead. And dwarf galaxies at the bottom. And from really early on, back in the early 1900s, people started to have this idea that maybe we can understand something about how these galaxies evolve if we start to classify them by what they look like. Maybe there's some evolutionary sequence we can extract from all of this. And this really started with Edwin Hubble back in 1936 making his really famous tuning fork diagram where he separated elliptical galaxies and spiral galaxies from each other. And he actually thought that the evolutionary sequence went from elliptical galaxies being kind of bland and not really having any interesting structure towards having a lot of structure and really unique arms and things like that. Turns out he was wrong. But there are a couple of things that we did learn from doing all of these galaxy classification studies. The first thing is that by doing all of these studies, we actually started to observe a whole lot of galaxies in our universe. And we observed so many, in fact, that we were able to make a big map of the universe. So in this map, you sort of sit at the center, and you point your telescope and kind of scan across this way, and you make a map where this is in distance away from the Earth. And what we found by doing this is that there are certain areas of the universe that have very low density. We call these cosmic voids. And in these cosmic voids, we find a lot of spiral galaxies, sort of like the Milky Way. So the Milky Way is a spiral galaxy. We live in what's called the local group, but it's actually a cosmic void. There's really not much going on here. We're not really in a very special place in the universe. In the high density regions of the universe, up here at the top, you can see a high density region, we find a whole lot of elliptical galaxies. So these are some of the things that we learned from doing these classification studies. Another thing that we learned is that there is actually an evolutionary sequence connecting these different types of galaxies. It's just not in the direction that Edwin Hubble thought. It turns out that if you merge two spiral galaxies, you briefly get an interacting galaxy, and then everything sort of settles down into an elliptical galaxy that's red and dead. And we actually don't only see this in observation, we also see this in simulation. So we can simulate the merger of just two spiral galaxies sort of left to their own devices. And you see here sort of two galaxies coming together. They're very disc-shaped. One's inclined to the other one. and they make their first pass. A little bit of the material gets kind of strewn about, but really the majority of the material in the center of these two galaxies comes together and it gets kind of thrown around and puffed up. And in the end, you get an elliptical galaxy that's essentially the mass of those two spiral galaxies combined. And this makes a lot of sense, right? Because we said that we see elliptical galaxies in really dense parts of the universe. And in a really dense part of the universe, you would expect there to be a lot of interactions and collisions and things like that. And it turns out that we can simulate not just one set of spiral galaxies interacting, we can actually simulate a whole chunk of the universe. So here in this simulation, we start off with a pretty uniform distribution of matter. You can see things collapse along these filaments that come out from the center. This filamentary structure is sort of the basis of our cosmology. And in the middle, you can see that there's a whole lot of interaction going on. There's collisions, there's gas being stripped off of different objects. And in the center of this whole big massive cluster, a very, very massive elliptical galaxy is being formed. And that's this bright thing right there in the middle. And you can see that as this simulation evolves, we really generate a lot of stuff around this elliptical galaxy, but there's really a distinct feature that this elliptical galaxy is most likely the most massive thing in that galaxy cluster. And the cluster that we form in this simulation is actually the size of one of the largest nearby galaxy clusters, the Coma cluster, which is the closest large cluster to the Milky Way. So just to recap, what we know about massive galaxies is that they probably form from lots of mergers and interactions. They present today as some of the most massive giant elliptical galaxies, and they live in some of the densest regions of the universe. What we also know about galaxy clusters is that they're home to a lot of interactions and galaxy mergers. They have a high fraction of elliptical galaxies compared to lower density regions of the universe. And galaxy clusters happen to be some of the most dense regions of the universe. So it only makes sense that if you want to find the most massive galaxies, you should probably look in the largest, most dense regions of the universe, which are galaxy clusters. So we'll take a step back to Earth for a second to illustrate a point. Pretend that you are an alien that has recently discovered the planet Earth. Good job, it might have life. You're really excited to find out. If it does have life, maybe you want to go down and say hello. So you find this planet, you're really excited. You pick this landmass in the upper left-hand corner to do your first initial survey for life. Okay, so you zoomed in. Because you're a creative alien, you'll decide to call this North America. And you think, okay, well, you know, I don't have that much time. I want to survey this landmass and see if there's life down there, see if I should even bother going down there and taking a trip. So you say to yourself, okay, I'm going to pick 3 random spots, and I'm going to take an image in those 3 random spots, and 3 random choices should give you a good idea of whether or not there's life, right? Right? All right, 3 random spots. Oh, man. There's no life on this planet. That's really unfortunate. It looked really promising. But, you know, that's okay. What if you had taken 3 different random images? If you took these 3 random images instead, you might conclude that, like, yay, there's life on this planet, but there's really not that much. It's sort of spread out. There's a couple of humans that live in these city things, but a lot of them sort of live in these kind of empty regions over here, like middle of the country, that kind of thing. So, okay, there's some people on this planet, but is it really worth your time going down there and checking it out? You don't really know. If instead you would have taken these 3 pictures, you would have concluded that this planet is teeming with life. These humans, they all live in really dense cities. Barely any of them live in the middle of the country. This planet has been overtaken by these humans. This poor rock, it's just suffering. So moral of the story, depending on where you take your random images, you might get a very different result. And of course, your result would change if instead of doing this in North America, you were doing this in South America or Asia or anywhere else in the world. So a better strategy would be to take one really big picture of the United States, North America as the aliens call it, and you would get a whole bunch of different diverse regions. So you would get some parts in the ocean where there's really not many people. You would get some parts in the west where there's, you know, a good population, but, you know, less than what's on the east coast. And you would really understand the diverse population of this planet and have a better census of the people that live there. And the same thing is what we do with galaxy surveys. So if you were to take 3 small area random surveys, sometimes you hit the jackpot, like with this one here in the middle. And other times you really just don't find much. You might not find the densest regions of the universe and find the most massive galaxies. So the strategy that you want to use is to take a really wide area survey of the sky so that you can really understand the different environments that exist in the universe and make sure that you pick up a large number of those overdense regions that host your massive galaxies. And at UT, we're doing exactly this. So here at UT, we have the Sheila ATX survey. Sheila is my namesake. So Sheila stands for the Spitzer ATX Exploratory Large Area. So this is a space telescope, this is a telescope in West Texas, and that's a large area. So this is a collaboration between the University of Texas at Austin, Penn State, and Texas A&M. And what you see here in this upper box, this background gray image is an image taken with the Herschel Space Telescope. And I just have it here because it's the bigger one, so it can be the background. But each one of these boxes, the green, orange, purple, and the pink circles, they each represent a footprint of a survey that was taken with a different telescope at a different wavelength. And there's a couple of very special things, too, in fact, about this survey that make it really, really great for finding a large sample of massive galaxies. And the first is that we observe at many, many different wavelengths. And the reason why we do that is to probe different properties about massive galaxies. I said that massive galaxies, we think they stop forming stars 3 to 4 billion years after the Big Bang. But we don't really know exactly when they stop forming stars. So understanding their star formation rate is really important. So that's why we observe in the UV, the optical, and the far infrared. It's also important that we identify the most massive galaxies in the universe by knowing how massive they are. So we observe in the near infrared to get a good handle on their stellar mass. The other really important thing about this survey is that it's a large area, so it doesn't really look, there's no real banana for scale here. But if you were to zoom in up into this corner, I promise you it's a very large area. This is the full moon. So across one of these circles, you can fit 4 of the full moon. So it's really a huge area that we're probing, and it's much larger than what people have been able to look at in the past, and that gives us a really unique perspective on massive galaxies. So I promised you a lot of massive galaxies. Here they are. So this is just one chunk sort of zoomed in even further of our survey. And because we have such a large area and a multi-wavelength survey, we're able to identify these objects. And so each one of these dots, each one of these big yellow dots and the small purple ones and the green ones, they're each a massive galaxy. And I've color-coded them by how massive they are. And I've made the circles bigger for the more massive ones just so you can see them easier. So like these ones over here are really, really massive. The stuff in here is really, really massive, but not as massive as these ones. So this really highlights the importance of having such a large area. Studies that have done this in the past, they observe maybe a chunk this big. And maybe they find a couple of massive galaxies, but maybe it's only 30 to 40 of these massive objects. With the survey that we're doing, we can find thousands, and we can actually start to do statistics with them and really understand this population. And with these statistics, we can actually divide up the universe into different time chunks. And we can start to ask questions like, when did massive galaxies stop forming stars? Is there an actual time in the universe that we can pinpoint where these things really stopped growing and haven't grown since? Or do they continue to grow all the way to the present day? What might cause these things to stop forming stars? Can theoretical models actually reproduce the observations, or do we need to work on the theory in order to match our observations? And with that, I hope I've convinced you that the most massive galaxies in the universe are pretty cool objects. They're rare, and they require very, very large area multi-wavelength surveys in order to study and understand what they're doing. Thanks.
Thank you, Agent of Sheila, Sydney Sherman. So we have some time for questions. Right here, sir.
All right, so the question is just how big is a massive galaxy? So they're about an order of magnitude larger than our galaxy, the Milky Way. So our galaxy is about 6 times 10 to the 10 solar masses. So that's just the stars in the galaxy, not necessarily with the black holes and things like that. These galaxies are about 5 times 10 to the 11 solar masses. So it's really a huge increase over the size of our galaxy.
Yeah, right behind there.
So the question is, how many light years across is our area? It's tough to do it in light years because it's that way. But we probe a volume that's orders of magnitude larger than what anybody has probed before. So the full moon is half a square degree across, or half a degree across, and ours is 24 square degrees. So it's a whole bunch of full moons.
Yeah. And sir, in the middle.
So the question is, if these are made from much older populations, are they made from much lighter elements? And the answer to that is that it's not necessarily that they have lighter elements or lower metallicities, but it's just that they built up that more metal-rich population a lot faster than anything else in the universe did.
Yes, right here.
So the question is, what is the assumption that these systems stop making stars? So the real reason why we think that they stop making stars is because we can find massive objects that are in the more local universe, and we find that they all have really old stellar populations, so stars that haven't, or galaxies that haven't formed stars in a very long time. So we date those stellar populations back to about 3 to 4 billion years after the Big Bang, and then that's how we expect these to no longer be forming stars.
So yeah, right here, last question.
Moving at the same speed after they combine and collide, or if they in fact slow down their rotation?
So the question is if the stars in the galaxies are moving the same speed when they're in a spiral galaxy or when they're in an elliptical galaxy. The answer is that they move at different speeds. The difference is in the way that you actually measure the speeds. So in a spiral galaxy, it's a very disky shape, so you measure just a circular velocity of those stars moving around the galaxy. And like our sun moves at 200-ish kilometers per second around the center of the Milky Way. For elliptical galaxies, things don't move in a nice ordered fashion. They sort of move in really random orbits around the center of the galaxy. So we actually measure what's called the velocity dispersion instead of just the circular velocity. So it's not really comparing apples to apples, but velocity dispersions are like 100 kilometers per hour, something like that.
Well, let's thank Sydney again